right. So for the fundamental questions on chapter 22, I picked the one about the electric field on the different regions on a cylindrical insulator. And it says we need to find the electric field inside and outside the cylinder, knowing that it's a non-conducting cylinder. And that's really important to know because if we know the difference between a conductor and an insulator, we know that those two are going to have different charges distributions, right? So if we have an insulator or a non-conducting material, then we know that the charges are going to be spread throughout the material, right? So the charges are going to be throughout, let's say the positive charge, and it's going to be placed throughout. If it's a conductor, which is a allows a good flow of charge, then it's going to have the charges on the surface only. Okay. So we are given that two variables R, and we are given the charge density P, which is basically the charge over the volume. And if we know the volume of the cylinder, it's just pi R squared times the length in this case and the charge. So that would be P. Okay, so in order to find, and I'm gonna draw it bigger. I'll go ahead and draw it bigger right here. I am going to find the electric field in a region like this, and in a bigger region outside of that area. Okay. So first for R, and let's call it lowercase letter r, for all smaller the r within that cylinder, then we can write an equation for the electric field. And for that, what I just did was the Gaussian surface, and that's going to allow me in a very easy way to find the electric field. And what Gauss law says is that the flux of the material is equals to the electric field times the area, and that's in turn equals to the charge enclosed by that surface divided by the constant. Okay, so for the radius smaller than for an area smaller than the original one, in this case in the cylinder, we have that the electric field is the charge divided by the constant times the area. Okay, so now what is the Q enclosed in that area? That's a good question, because we have that Q can be found by moving all this right here to the other side, and we get that the charge density times PR square pi r squared times the length is equals to Q, right? But then since we're finding the electric field on that one, we can go ahead and put the area as well of that Gaussian surface that we're doing, pi L squared. Now, it's important to notice that in this case, the R's, either inside and outside, are actually going to cancel, because they are going to be the same. So we are going to have this one right here on top, and it's going to be R divided by E, this case 2. And that would be the electric field inside of that cylinder for an area smaller than that. Now, for outside, for an area outside, is going to be a little bit different, because now we have a larger area, right? So we can still use the same formula, enclosed divided by the area. And then this is not going to change because we have 2 pi r times the length. And this r, the difference is that this r is going to be larger in this case, right? So what's gonna happen is that when we find the Q enclosed by that whole cylinder, we have that would be pi r squared. And it's gonna form, in this case, they are going to be different. So the Q enclosed would be the whole thing on top like we found for Q. So it would be pi r squared times the length times the density. And the only things that are going to cancel out the length, pi, and we get something like this, r squared by 2 the constant times the radius. And that will be the electric field for inside and outside. All right.